Well, hello there. My name is Zima Abdul Karim. My ID is 5643908, and I decided to go with experiment 1, understanding the solar system. In this experiment, we will go through celestial bodies with different masses and analyze the changes affected upon them with respect to Kepler's law of planetary motion. So before we dive into the simulation itself, let us go through Kepler's law one by one. Starting off, Kepler's first law is the law of ellipses, which states that every planet orbiting the Sun is in an ellipse, and the Sun itself is one of its focus points. This means that the orbits are not perfect circles. Okay, moving on. Kepler's second law states that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time, which means that when the planet comes close to the Sun, its radial vector shortens, and to keep angular momentum the same, its tangential velocity increases, and while it's moving away, is the vice versa of it. And Kepler's last law for planetary motion is Kepler's third law. It is actually a very fascinating mathematical equation, which is t squared equals to 4 pi squared a cubed divided by gm. Here it states that the orbital period of a planet should be proportional to the semi-major axis of that planet's orbit. In a two-body system, both objects share a same. Okay, in a two-body system, both objects orbit a shared center of mass, which is known as the barycenter. In the case for the Earth and the Moon, it is 4,700 kilometers away from the Earth's surface. This offset makes the Earth wobble a little bit. If we look at the simulation on the screen, we could see that the Earth wobble a little bit and leaves a smaller loop, whereas the Moon leaves a bigger loop. This is due to Newton's third law. In here, we can see Newton's third law as the gravitational force exerted by the Moon on the planet is the equal and opposite of the gravitational force exerted by the planet on the Moon. This motion makes the two objects come closer. Across question 1, 4, and 7, we could see that the center of mass always lies within the Sun due to its massive mass. Even in question 4, where we increase the mass of the planet by 2 folds, the barycenter and the center of mass always lie within the Sun. In question 4, however, we did do something different. Here, we increase the mass of the Sun by 2 folds and lower the tangential velocity of the planet, which resulted in the planet spiraling towards the Sun. In this part, we're going to do some maths. In the planet moon versus star planet system, the key difference lies in their mass ratios and distances. In a sun earth pair, the star's immense mass places the barycenter deep within the sun, making it appear stationary while the planet orbits. If the masses were closer, the barycenter could even lie outside both bodies, so greater separation would also shift the barycenter further from the larger object. Let's explore how to calibrate the distances using the simultaneous measuring tips. 1 grid corresponds to 73 million kilometers, which is roughly around 0.5 astronomical units. So this means that the two grid line equals roughly 1 astronomical units, with 2% off from the official value of 149,597,870 kilos. It shows a distance of half, 1, 1.5, and 2 astronomical units here. After matching the orbital velocities to create a roughly circular orbit, a clear trend could be seen here. These orbits, despite looking circular, are slightly elliptical and are representative of the shape of the Earth's orbit. This is due to Kepler's first law, stating that every planet orbit around the Sun is elliptical. In these cases, the eccentricity of the orbit is very small, making its shape nearly circular. Although I adjusted the tangential velocity in order to get a circular object, we can see that the orbital period stretches from 132 days up to 1012 days. So to check this relationship, I had to compare the Newtonized formula for each orbit and compare it to Earth's ideal value of 133,325. As according to the third law, this should be the constant at every orbital distance around the same central mass. Now coming over to this, in simpler terms, the farther a planet is from the Sun, the longer it takes to go around once, and the slower it moves. The slower it moves. This is a direct consequence of Kepler's third law and the orbital velocity equation v equals to square root of gm over r. For example, Mercury at just 0.39 astronomical units from the Sun shoots along its orbit at about 47.9 kilos per second and completes a year in only 88 Earth days. By contrast, Neptune lies more than 30 astronomical units away and crawls around the Sun at only 5.5 kilos per second. Talking about 165 Earth years to finish a single orbit. So Mercury, being the closest to the Sun, is thereby the fastest planet, and Neptune being the farthest had the slowest orbital speed and the longest year. Okay, so what did I learn? I think the main thing that I learned is the even scale of a solar system, and that orbits are not circular as I thought growing up watching cartoons. And I just also learned the barycenters, the Keplers, Kepler law and the orbital motion. That's the main thing. And thank you for giving me this opportunity. And yeah, keep exploring the stars.